The Artemis II crew came home different than they left. On April 10, 2026, 4 astronauts splashed down in the Pacific Ocean off the coast of San Diego after spending 10 days farther from Earth than any human being in history. Reed Wiseman, Victor Glover, Christina Cook, and Jeremy Hansen had just completed a loop around the far side of the Moon aboard the Orion spacecraft, reaching a maximum distance of 252,656 mi from home. They broke the record set by Apollo 13 in 1970. They captured over 7,000 photographs of the lunar surface. They watched the sun disappear behind the Moon from a vantage point no human eyes had ever occupied. And for all of that triumph, the most quietly extraordinary thing about the mission was what it did to their bodies. Because 10 days in deep space is not a vacation. It is a controlled demolition of everything your body assumes about the world. The changes start within hours, not days, hours. The moment the Space Launch System's engines cut off and the crew reached orbit on April 1st, gravity stopped pulling their blood and body fluids downward. On Earth, roughly 2 L of fluid sit in your legs at any given moment, held there by gravity the way water settles to the bottom of a glass. Remove the gravity, and that fluid has nowhere to go but up. It floods into the chest and head almost immediately. The face swells, the sinuses clog, the legs thin out. Astronauts have a name for it that sounds almost funny until you think about what it actually means. Puffy face, chicken legs. Within a few hours of reaching orbit, the Artemis II crew would have looked noticeably different from their launch day photos. Swollen cheeks, narrowed eyes, congested noses. Their legs would have started to shrink as fluid drained out of them. If you saw a photo of an astronaut on day 3 next to their official crew portrait, you would think they were sick. They weren't sick. Their bodies were doing exactly what they're built to do, adapting to their environment. The problem is that the environment was lying to them. Your cardiovascular system is an engineering marvel that evolved over hundreds of millions of years to solve one specific problem: pumping blood uphill against a constant gravitational pull. Your heart, your veins, your arterial valves, your leg muscles, all of it is calibrated to fight gravity every second of your life. Take that gravity away, and the system doesn't break. It recalibrates. Your heart, suddenly having no hill to pump against, begins to shrink. Not from disease, from efficiency. A smaller heart is all you need. When there's no resistance, your body, in its ruthless pragmatism, starts downsizing the one organ you cannot afford to lose. On a 10-day mission, the shrinkage is measurable but modest. On a 6-month mission aboard the International Space Station, it becomes a serious medical concern. The Artemis II crew was lucky in this regard. 10 days was enough to start the process, but not long enough to make it dangerous. The danger comes later on the ground, when that shrunken heart suddenly has to pump against full Earth gravity again. Recovery teams were waiting in the Pacific for a reason. The crew wasn't walking off the helicopter unaided, at least not comfortably. Then there's the skeleton. Bone is not the dead scaffolding most people imagine. It's a living tissue constantly being torn down and rebuilt by 2 types of cells that work in opposition. Osteoclasts dissolve old bone. Osteoblasts lay down new bone. On Earth, the balance between these two is maintained by mechanical stress. The weight of your own body pressing down on your skeleton every time you stand, walk, or climb a flight of stairs. That stress tells your bones to stay strong. It's a signal, a demand. Stay dense, or you'll shatter. In microgravity, the signal vanishes. Your skeleton is no longer bearing load. The osteoclasts keep dissolving bone at their normal rate, but the osteoblasts slow down because there's no demand for new construction. The result is a net loss of roughly 1 to 1.5% of bone mineral density per month. concentrated in the weight-bearing bones of the hips, spine, and legs. That rate is roughly equivalent to what a postmenopausal woman with osteoporosis loses in an entire year on Earth, compressed into 30 days. On the space station, astronauts exercise for 2 hours daily on treadmills and resistance machines specifically to fight this. The Artemis II crew had a flywheel exercise device inside Orion, a cable-based system that supported rowing, squats, and deadlifts. But Orion is about the size of a camper van. 2 hours of structured exercise in a camper van shared with 3 other people while floating is not the same as 2 hours in a gym. 10 days isn't long enough for catastrophic bone loss. The crew didn't come home with brittle femurs, but measurable changes at the cellular level begin within 72 hours. Mouse studies have shown functional bone loss as early as 3 days after exposure to radiation doses comparable to a solar flare. And the Artemis II crew wasn't just dealing with microgravity. They were dealing with something the International Space Station astronauts are largely shielded from: radiation. This is where Artemis II separated from every crewed mission of the past half-century. The ISS orbits inside Earth's magnetosphere, the magnetic bubble that deflects most of the high-energy particles streaming in from the Sun and from deep space. It's not perfect protection, but it's substantial. The Artemis II crew left that bubble. They flew through the Van Allen radiation belts on the way out and again on the way back, regions where trapped electrons and protons swirl at tremendous energies. And for the days they spent between Earth and the Moon, and on the far side of the Moon, they were exposed to the full deep space radiation environment, galactic cosmic rays, and whatever the Sun decided to throw at them, with nothing between them and those particles but the aluminum and composite walls of the Orion capsule. Orion carried 6 radiation sensors throughout the spacecraft, and each crew member kept a personal dosimeter in their pocket. If the Sun had unleashed a powerful solar particle event during the mission, those sensors would have sounded warnings, and the crew would have sheltered in the most heavily shielded section of the capsule. The Sun cooperated this time. It stayed relatively quiet, but quiet doesn't mean safe. The total dose for the 10-day mission was modest, by career astronaut standards, roughly equivalent to a full-body CT scan. That sounds manageable, and for a single mission, it is. The concern isn't what one CT scan does to you, it's what that exposure reveals about longer missions. The radiation in deep space is qualitatively different from what astronauts encounter in low Earth orbit. Galactic cosmic rays include heavy ions, atomic nuclei stripped of their electrons and accelerated to enormous speeds that punch through shielding and through cells in ways that low-energy radiation does not. A single heavy iron ion, and iron alone accounts for about 13% of the dose equivalent from galactic cosmic rays, can tear through a cell like a bullet through paper, shredding DNA in ways the cell's repair machinery struggles to fix cleanly. The damage isn't always lethal to the cell. Sometimes the cell survives with errors in its genetic code, and those errors can accumulate over time into something worse. NASA knew this going in. That's why they designed one of the most unusual experiments in spaceflight history to fly alongside the crew. Mounted on a wall inside the Orion capsule were a set of small devices, about the size of a USB thumb drives. Each one contained living human bone marrow, grown from cells donated by the astronauts themselves before the flight. The experiment was called Avatar, a virtual astronaut tissue analog response. The idea was elegant and slightly unsettling. Scientists at Harvard's Weiss Institute had taken platelet samples from Wiseman, Glover, and Hansen, extracted the bone marrow stem cells, and cultivated them onto organ-on-a-chip devices that replicated the structure and function of human bone marrow. These chips flew the same trajectory as their human donors, absorbing the same radiation, experiencing the same microgravity for the entire 10-day mission. Twin chips remained on the ground as controls. Bone marrow was chosen deliberately. It's one of the most radiation-sensitive tissues in the human body. It produces red blood cells, white blood cells, and platelets. Damage it, and you compromise the immune system, the blood's ability to carry oxygen and its ability to clot. When the chips return to the lab, researchers will perform single-cell RNA sequencing to map how thousands of individual genes changed during the flight. The results will be compared to the ground controls and to blood samples taken from the actual astronauts before and after the mission. Nobody expects the Artemis II crew to show signs of radiation sickness. The dose was too low for that. What researchers are looking for is subtler molecular signatures of stress, early indicators of accelerated aging in the cells, changes in gene expression that might over a longer mission cascade into something clinically significant. The Avatar chips are a preview, a way to see the future of deep space travel written in the biology of 4 people who spent 10 days living in it. Meanwhile, inside their own bodies, other changes were accumulating in ways the crew could feel. Muscle atrophy begins fast. Without gravity to resist, the muscles in the legs and lower back, the ones that spend all day on Earth keeping you upright, start to wither. Astronauts on longer missions can lose up to 20% of their muscle mass in as little as 5 to 11 days. The Artemis II crew was right in that window. The flywheel helped. Daily exercise sessions where all 4 crew members took turns rowing and doing resistance movements kept the worst of the atrophy at bay. But the flywheel weighed just 30 lb and was about the size of a carry-on suitcase. It was designed to meet strict mass and volume constraints. You don't get a squat rack in a spacecraft smaller than most studio apartments. The muscle loss isn't just about strength. The type of muscle fiber changes. Slow-twitch endurance fibers, the ones that keep you standing all day, begin converting to fast-twitch fibers. This is your body rewriting its own hardware for an environment where endurance doesn't matter and quick bursts of movement do. Practical for floating through a spacecraft, terrible for walking on Earth. And then there are the eyes. Roughly a third of astronauts on long-duration ISS missions develop a condition called spaceflight-associated neuroocular syndrome, or SANS. The fluid that shifts toward the head in microgravity doesn't just puff up the face. It increases intracranial pressure, the pressure of cerebrospinal fluid inside the skull. That pressure pushes on the back of the eyeballs, flattening them slightly, swelling the optic nerve, and causing farsightedness. Some astronauts who had perfect vision their entire lives suddenly need reading glasses in space. Some experience changes that persist for months or even years after landing. For a 10-day mission, full-blown SANS is unlikely. The more severe structural changes to the eye take weeks or months to develop. But the fluid shift is immediate, and the pressure increase begins on day 1. The Artemis II crew tested an orthostatic intolerance garment on the return leg of the trip, a piece of clothing worn under their spacesuits designed to help maintain blood pressure and circulation during the transition back to gravity. That garment exists because the return is where the body's recalibration turns hostile. All those adaptations that made sense in microgravity, the shrunken heart, the redistributed fluids, the relaxed blood vessels become liabilities the moment gravity returns. When Orion hit the upper atmosphere at roughly 25,000 Artemis, the crew experienced a 6-minute communications blackout as plasma formed around the capsule during peak heating. The heat shield, a subject of intense debate before launch after issues discovered during the uncrewed Artemis I test flight, absorbed temperatures that would melt steel while the crew sat meters away behind it. They endured up to 3.9 Gs during re-entry, nearly 4 times the force of gravity pressing them into their seats. For bodies that had spent 10 days without any gravitational load at all, that transition was violent. Imagine spending 10 days floating in a warm pool, weightless, your muscles relaxing, your heart easing off, your entire circulatory system resettling into a new equilibrium. Now imagine someone strapping you to a chair and dropping you from a cliff. That's an exaggeration, but the physiological whiplash is real. The heart had to pump harder than it had in over a week. Blood that had been floating freely in the upper body suddenly crashed back down into the legs. The vestibular system, the balance organs in the inner ear that had spent 10 days with no reliable gravitational reference, was suddenly overwhelmed with input. About half of all first-time space travelers experience severe motion sickness in orbit. The return can be just as disorienting. Standing up after splashdown without assistance would have been difficult. The recovery team extracted the crew from Orion in open water, transferred them to an inflatable raft, and helicoptered them to the USS John P. Murtha. Post-mission medical evaluations began immediately on the ship. The crew will spend weeks in post-flight reconditioning. Their muscles need to relearn how to fight gravity. Their cardiovascular systems need to readjust to pumping blood uphill. Their bones need the mechanical stress of walking and standing to signal the osteoblasts to start rebuilding. Their balance systems need to recalibrate to a world where down is a fixed direction again, not a concept that changes every time you turn your head. And here's what makes all of this quietly extraordinary. This was 10 days. 10 days of weightlessness, 10 days of radiation exposure, 10 days in a spacecraft the size of a small RV. And the list of physiological changes is already this long. The muscle atrophy, the bone demineralization, the fluid redistribution, the cardiovascular deconditioning, the vestibular confusion, the cellular stress from radiation, the potential early signatures of accelerated aging. All of it began within hours and accumulated every day of the mission. NASA has plans for missions lasting months. Artemis IV aims to put astronauts on the lunar surface in 2028 for extended stays. Mars missions would take roughly 3 years round trip. 3 years of everything the Artemis II crew experienced in 10 days, magnified and compounded. The bone loss alone would be staggering. 18 months at 1 to 1.5% per month means an astronaut arriving at Mars could have lost a quarter of their hip bone density. The radiation exposure would accumulate far beyond the CT scan equivalent of a lunar flyby. Galactic cosmic rays don't stop. They don't take days off. And there is no magnetosphere between Earth and Mars. The Avatar experiment matters precisely because of this timeline. If scientists can identify the molecular changes, the 10 days of deep space caused in personalized bone marrow models, they can begin predicting what 30 days would do, what 90 days would do, what 3 years would do, and more importantly, they can start designing countermeasures, drugs, supplements, shielding strategies, exercise protocols tailored to each astronaut's individual biology. Dr. Stephen Platts, NASA's chief scientist for human research, described the overarching hazards of spaceflight with a single acronym: RIDGE. Radiation, isolation, distance from Earth, gravity, environment. Every one of those hazards was present during Artemis II, and every one of them left a mark. The crew also participated in an immune biomarkers investigation, blotting saliva onto specialized paper booklets since Orion had no refrigeration. Those samples will reveal whether deep space conditions reactivated dormant viruses in their systems, a phenomenon observed in ISS astronauts where latent herpes viruses flare up under the combined stress of microgravity and confinement. Spaceflight suppresses the immune system. The exact mechanisms are still being studied, but the pattern is consistent. Astronauts get sick more easily in space, their wounds heal more slowly, and viruses that have been dormant in their bodies for years sometimes wake up. 10 days may not be long enough to see the full effect, but the saliva samples will tell the story. Wrist-worn actigraphy devices tracked their sleep patterns and behavioral performance in real time. In a capsule barely large enough for 4 people to sleep, eat, and work without bumping elbows, sleep quality is not a given. The absence of a natural daylight cycle, the constant hum of life support systems, the knowledge that you are farther from home than any human has ever been. All of it compounds. About 70% of astronauts report headaches in space, even those who never get them on Earth. The likely culprit is a combination of elevated intracranial pressure from fluid shifts, impaired venous drainage from the brain, and slightly elevated carbon dioxide levels in the cabin atmosphere. A headache you can't escape in a room you can't leave while floating in a place where the nearest hospital is 250,000 miles away. That's not just a medical issue, that's a psychological one. NASA's behavioral researchers were watching closely. The ARCA study monitored the crew's teamwork dynamics, cognitive performance, and stress levels throughout the mission. 4 people in a space the size of an RV for 10 days performing complex tasks while their bodies silently reconfigure themselves represents a psychological pressure that no amount of underwater training or cave exploration can fully replicate. Jeremy Hansen had spent a week living deep underground in an Italian cave as preparation that helped with the confinement. It couldn't prepare him for the radiation. Christina Cook has experience with long-duration spaceflight. She spent 328 consecutive days on the ISS in 2019 and 2020, the longest single spaceflight by a woman at the time. She knows what microgravity does to a body over months. For her, 10 days was a sprint. For the others, it was their first time experiencing what it feels like when your own biology turns against the environment you've chosen. There's a small detail that rarely makes it into the dramatic accounts of spaceflight, and it's this. Food tastes different in space. The fluid shift toward the head congests the sinuses so thoroughly that astronauts report everything tasting muted like eating with a bad cold. The Artemis II menu included 58 tortillas, barbecued brisket, vegetable quiche, spicy green beans, 5 varieties of hot sauce, and condiments ranging from maple syrup to Nutella. The hot sauce wasn't an indulgence, it was a necessity. When your taste buds are effectively muffled by the same swelling that puffs up your face, you reach for the strongest flavors available. The crew rehydrated freeze-dried meals using Orion's water dispenser and heated them with a briefcase-sized food warmer. Eating in microgravity, where crumbs float into instrument panels and liquids form wobbling spheres that drift toward electrical systems, is its own kind of operational challenge. Every meal is an exercise in controlled chaos. In January 2026, while aboard the International Space Station, NASA astronaut Michael Frink suddenly lost the ability to speak for roughly 20 minutes. Mission controllers ruled out a heart attack and choking, but the incident was alarming enough to end his mission early, one of the rarest medical evacuations in the history of the station. The Artemis II crew was farther from help than Frink. If a medical emergency had occurred on the far side of the moon during those 40 minutes of communications blackout, when the moon itself blocked all contact with Earth, there was no rescue option. No abort, no emergency return in time to matter. The crew carried medications and basic medical supplies. They did not carry a surgeon. What returned to Earth on April 10th was 4 people who looked from the outside mostly like themselves, a little puffy, a little unsteady, smiling in their orange survival suits as they were pulled from the water. But beneath the surface, at the level of cells and fluids and bone mineral density and gene expression and cardiovascular tone, they were measurably, quantifiably different from the 4 people who had launched 10 days earlier. We sent them to the moon and brought them back. The question that Artemis II was really asking, the question that all those experiments and all those saliva booklets and all those tiny bone marrow chips were designed to answer, is whether we can send people much farther for much longer and still bring them back whole. The data from this mission won't provide a final answer. It will provide a first draft. And in that first draft, written in the biology of 4 astronauts who spent 10 days in the most hostile environment any human has entered in over 50 years, we might find the beginning of a map for everything that comes next. Thanks for watching, and I'll see you in the next one.